All right, welcome back. This is video number 2. If this is not the second video you are watching of mine, you are in the wrong order. Go back and find the first video. All right, so temperature and rates. Obviously, we know that kinetics are affected by temperature. And as temperature goes up, the rate goes up. Temperature and rate are directly proportional as far as how they affect one another. And the easiest way to see this is to actually examine glow sticks. So, and let me say it now. Do not microwave glow sticks. Don't do it. The chemicals in a glow stick are poisonous, and if you microwave them, the plastic will melt and that poisonous chemical will explode all over the microwave, and then the next time you cook something in there, it's going to get in your food, and then you're going to eat it, and you're going to poison yourself. Don't do it. Also, don't be one of those dumb people who puts glow sticks in their mouths. Please don't do that. Poison. Poison, people. Poison. Okay. All right. But here's, look at the picture. So we've got a glow stick that's in hot water and a glow stick that's in cold water. Now that you can do if you're curious. Boil some water and then stick a glow stick in it. It makes it super bright. But put the glow stick in the heat, in the hot water. Don't just microwave the glow stick, okay? But yeah, it gets to glow really, really, really bright, which is super cool because glow sticks are a luminescence reaction, okay? Which means electrons are shooting around and relaxing and letting off this energy, which we see through the glowing. But while it's super bright, that glow stick's not going to last as long. Okay, so it may be more entertaining, but it's going to be more entertaining for a shorter period of time because that glow stick only has X amount of chemicals, and this is not a reversible reaction. That's why glow sticks die. I mean, there's only X amount of chemicals, and when they're all run out and the reaction has hit completion, it's over. There's no way to reverse it. You just throw it away and get a new one, right? So while you can heat it up and make it more fun, it's not going to last as long. Okay, but if you put it in ice, or if you were like me when you were a kid and you went to the roller rink and you threw your glow stick in the freezer when you got home, it still had some juice the next morning because you slowed it down enough where it didn't run out overnight. So interesting. It's the proof that temperature affects rate, and we can see it through something really cool that everybody likes. Now, but let's talk about how that relates to rate laws. So we know that rate is equal to K times the concentration of reactants, or maybe not, right? If it's zero order overall, the concentrations make no difference, right? But if it's first order, second order, third order, it does, right? So that means, since not all concentration units are temperature dependent, K has to be temperature dependent. And I'll prove that to you by showing you a plot. So in this plot, we have temperature on the x-axis and K on the y-axis. And as temperature goes up, K goes up. It's a linear relationship, which is why rate and temperature have a linear relationship, because rate and the rate constant have a linear relationship based off the rate law. But this isn't just the like normal increase, right? This isn't a linear increase. This is an exponential increase. So yes, temperature definitely affects rate in a very big way. Essentially, the rate constant is going to double every time the temperature increases by 10 degrees, which is huge. So absolutely temperature dependent. And if we think about it, what we're trying to say here is that there's energy associated for a reaction to take place because bonds have to break before they can form in some cases. To break a bond, that requires energy. How are you going to, where's the energy coming from to break the bond in the first place so that you can reform the new bonds? So I will show you a picture that comes from a textbook, not yours, previous textbook we use, which is the most preposterous looking picture I've ever seen in my life. If anyone went to a golf course and it looked like this, no one would go to that golf course. I mean, come on. I don't even see how you could angle that to get into the hole. I mean, just the amount of energy it would take to get over that stupid mountain in the middle of the golf course, it'd shoot way past the hole. But nonetheless, imagine this was less ridiculous and it wasn't all the way up to her waist, okay? Imagine we're in a goofy golf scenario, right? Some people are good at goofy golf, some people aren't. Because and when I say goofy golf, I mean, what's the term that other people use? Mini golf. Okay, I call it goofy golf. But nonetheless, you want just enough energy to get it up the hill to start doing all of its wacky doodle stuff, whatever it's going to do, depending upon the course. But you don't want to hit it with too much energy because then you're just going to shoot it out of the little area, or too little energy and you're my mom and you just spend 6 shots unsuccessfully getting it over the first hill. Okay, so because there's a minimum amount of energy it takes to actually get it up there to where you can then start actually playing the mini golf game. Okay, we call this minimum amount of energy the activation energy, and we represent it as a capital E with a subscript A. Okay, so this is the minimum amount of energy it takes to start a chemical reaction. And this could be really high or really low. It honestly depends upon the reaction itself. But I want to be very clear here. This is an energy association, but we are talking about kinetics. So this energy will relate to speed. And I'm going to show you how this energy relates to speed. And you can honestly think about it. The bigger the hill, the more time it's going to take you to gather up that energy, right? The smaller the hill, the less time it's going to take you. So huge activation energies, that's going to slow you down, right? Small activation energies doesn't really slow you down near as much. Okay, so let's look at an example of this. So what you're seeing on the slide right now, we call this a reaction coordinate diagram. And I actually showed you this reaction previously in the PowerPoint, but now we're actually looking at the mechanism of how it happens. So we're going from this compound right here, where the methyl group is attached to the nitrogen, to this one, where the methyl group is attached to the carbon. So you see what happens is you got to break this bond first. So this needs to rotate to break the bond. That is breaking a bond. That requires energy. So as this reaction proceeds, the potential energy is going way up. Here's our activation energy right here. How much energy it takes to break this bond and enter this point on the graph. And we call this point the transition state. And at the transition state, you find something called the activated complex, which an activated complex and transition state, sometimes those words are interchangeable, but this is not stable. Okay, you will not stay in this position. Imagine that this is almost like a point. There's no place to stay. You can either go this way or this way, but you can't live up here, right? So this is an unstable complex. Then it's going to keep rotating, and we're going to start forming the bond we want to form. Forming bonds releases energy. So we're progressing forward in our pathway. We're going down in energy until we reach our new complex. So then my question is this. If we started here in energy and we ended here, we started higher and we ended lower in energy, is this an endothermic reaction, meaning energy had to be put into it, or is this exothermic? And it's kind of a confusing question. It is technically exothermic. All reactions require energy on the front end. But how you determine if something is endo or exothermic is you look at a cost-profit analysis. It cost you the activation energy, but you gained the activation energy plus this difference in energy. So this difference in energy is your profit margin. So you profited this much in energy. So this is an overall exothermic reaction. And this slide is just something I put in the notes. It basically is saying everything I'm saying, so I'm just going to shoot right past it. You have it in the PowerPoint on the class page, okay? All right, but let me go back. Okay, but while one direction is exothermic, if you were to flip this, then it would be endothermic, right? Because you're starting lower in energy and you're ending higher in energy. And if you go in the reverse, then all of this would be the activation energy. All right. Okay, cool. All right, going back forward. Okay. Let's look at this. So this is an example of a Maxwell-Boltzmann distribution. Okay, and what a distribution is a distribution recognizes that if molecules are moving, and molecules always are, unless we are at absolute zero, they're not all going to be moving at exactly the same speed because they don't all have exactly the same kinetic energy, because some of them are ramming into one another and the wall and losing a little bit, and some of them have a little bit more. So we represent things as, or the fraction of molecules with respect to kinetic energy, as a distribution. So for this lower temperature, most of them are in this range, but a few of them, tiny margin, have the minimum activation energy needed for the reaction to proceed. So when you heat something up, you're not shifting the entire curve over. You still are relating to this sort of T0 point, but what you've done is you've broadened the curve, or you have flattened the curve and allowed for more to have the ability to have the minimum activation energy required. Let me relate this to something that is very relevant in your life right now. You may have seen in the news that the whole point of us doing this distance learning, is the idea of social distancing. And what social distancing does is it doesn't necessarily decrease the number of cases of this virus. But what it does is it flattens the curve. So instead of it being a huge spike of sick people all at once when the hospital can't handle it, it takes this curve and it flattens it out over a longer period of time. So yes, it sadly means the virus may last longer, but it means that more people will more likely survive it because the hospital resources won't be overwhelmed. Just thought I'd give you a more recent example of why we care about Boltzmann distributions. Okay, but we can relate this idea of energy and how it relates to a rate law through K by using the Arrhenius equation, which you've actually seen this guy before. This is not the first time I've told you about this chemist. He's the guy who developed the first acid-base theory. Okay, that acids increase the concentration of protons in water, bases increase the concentration of hydroxide ions in water. This is that guy. Okay, so he actually had several really cool discoveries. But he helped us develop this relationship right here, which you do not have to memorize. But we see how K, the rate constant, relates to EA, the activation energy. So K is equal to A. Now what's A? A is what we call the frequency factor. And we'll talk more about this in the next video, but the idea of the frequency factor is that it accounts for the likelihood of having a successful collision. And we'll talk about the difference between unsuccessful and successful collisions later on, but it accounts for a high frequency factor, lots of successful collisions. Low frequency factor means not a lot of successful collisions. And then this E is not necessarily just the letter E, it's inverse natural log, okay? So the opposite of a natural log, so E to the negative activation energy divided by R and divided by T. But this is not the R that you've seen before, okay? This is not 0.08206 liter atmosphere per mole Kelvin. This is 8.314 joule per mole Kelvin. But if you remember, I taught you a conversion factor between liter atmospheres and joules when we did the thermo chapter, right? Because work was equal to negative P delta V, and that was a pressure times a volume, so you ended up getting a liter atmosphere, and then you multiplied by a factor to turn that into joules. If you don't remember what that factor was, the factor was 101.3. There are 101.3 joules in every 1 liter atmosphere. So now in your calculator, take that R that you know and love, 0.08206, multiply by 101.3, and lo and behold, you get what's on the slide. Okay, so that's where this number comes from. R is R. It's just we've changed the units of it. That's all. But it's still the same R that we all know and love. Okay? All right. So that's the end of this video. I will see you again in video 3.